Right, so welcome back for those GPU people who just can't get enough GPUs and you want it to stay. Excellent. Whoop, whoop. Yeah, all that. Right, so what we're going to do is, I had to change the slide because it's not advanced optimization approaches. And initially this said deep dive, and it's not that deep. It's it's a little bit deep. We're going to look at more than what we did last time, but it's not possible really to go into kind of really deep optimization without kind of a bit more understanding of the GPUs, and that would take another couple of days, I think. So what we are going to do is we're going to look at some kind of common things that we can do that would apply to kind of any GPU code that you write. Of course, the right way to kind of improve code is not to kind of optimize it in advance. The right way to do it is to kind of profile your code, understand where the bottlenecks are, and then optimize and go through a cycle of doing that. But the things that I'm going to propose here are things that you should just do anyway, right? So these are kind of optimization approaches that you should consider when writing any GPU code, because they're going to have an impact on the performance. And it doesn't matter whether that would be GPU code, actually, or a lot of these would apply to CPU code as well. So the first thing does actually only apply to GPU code, and it's data transfer. So in the previous set of slides, so it wasn't yesterday, it was the day before, wasn't it? I talked about data transfer. So when we write a GPU kernel, what happens is we're moving data onto the device, performing some compute, then we're moving the data back. The cost of that movement is potentially quite expensive. So we want to hide that movement as much as we can by doing lots and lots of compute when we've got stuff on the device. In fact, this is a general optimization technique anyway. As kind of GPUs become more and more parallel, you can think about that rate of change that I mentioned the other day, that the flops are becoming increasingly more available. The real challenge is moving data. So what we're really trying to do is solve a problem of minimizing data movement, and that's kind of at all levels of the GPU. And the first level is this moving data to the device and back off again. So I've kind of highlighted here, the first optimization technique is minimize data copies. Keep data on the device as long as you can, perform as much compute on it as you can, and it may be quicker to recalculate data on the device than to kind of move things kind of backwards and forwards. So, just to check and see whether anyone's paid attention to what I've said there, I have two examples of code which you can probably just about read. I'm just going to turn that light. Could you turn the light switch off? Is that a light switch? It is, yeah, go for it, see what happens.
It takes a while.
Yeah, there we go, okay. So there's two examples of code here, and I'm going to ask you in a moment, which of these approaches minimizes data transfer? So first one, loops over time steps, does an inexpensive routine on the host, copies data from the host to the device, expensive routine on the device, data back, and then it goes through another loop. The second one, copies data to the device, loops over the time steps, does an inexpensive routine on the device, an expensive routine on the device, and it does that within the loop and then copies back at the end. Which is the good one? Top or bottom? Bottom. Who thinks bottom? Anyone disagree with that? Of course not. There we go. Well done. You've passed the first test. There are more tests, so please do pay attention. So that's a fairly easy one, right? We want to minimize data transfer. Okay. So next, device utilization or device underutilization, right? So yesterday I made this point of what we want to do is oversubscribe the device. So this concept we had of a grid of thread blocks, what we want to do is have more blocks than there are streaming multiprocessors, more threads within the block than there are cores within the streaming multiprocessor. We constantly want to oversubscribe. So one of the reasons that we do that is that one of the reasons that we want to do that is that we want to be able to try and hide things like memory latencies. So when we have a piece of GPU code and it says go and fetch something from memory, what's actually happening there is it's sending a memory request, it's issuing an instruction that's causing memory to have to move from the GPU's global memory through the different cache levels into registers. And that's really slow. So it's really high bandwidth, yeah, but the latency is like really big, it's really long, it's slow, right? So the GPU counteracts that by having lots of parallelism available. So when we hit an instruction that says, go and get me some memory, that thread, the threads that have issued that effectively stall. And they say, well, we can't do anything now. We're going to sit here, we're stalled. you know, we're all doing the same thing, we're all in parallel, but we're all stuck, we're all waiting for that memory to come back. So what the GPU does is it context switches and it says, right, that's stalled, fine, go away. We'll switch something else in, we'll switch another group of threads in, and because we've got more than there are cores available, because we've oversubscribed, we can do that. We can context switch something else in and then see if there's some useful instructions we can do. And if that one says, go and get me some from memory, guess what it does? It goes, right, you can go back again, we'll have another. And it's constantly doing this. And the context switching is free. It's not something that you program. It's just something that's happening and kind of behind the scenes. And it's the way that the GPU masks kind of latency. So there's a couple of kind of implications for this. So you need to make sure you've oversubscribed. You need to make sure you've got as much parallelism as possible. And no, I'll save that for a moment. Okay, so yeah, so latency, it's a couple of hundred cycles. You're much better off, and it's a slightly different optimization technique, really, that is kind of try to do as much compute as you want, because the more compute you do in your threads, the less kind of you have to wait on things that have stalled. Obviously, you can get to a point where, you know, you might have lots and lots of threads. You might have oversubscribed a lot, but if fundamentally what you're doing is requesting memory, you might go through everything that's kind of oversubscribed, switching them in, and then all of them end up stalling and waiting. Yeah, so you may end up kind of latency bound, and nothing's going to make that fast. Because yeah. So the optimization technique then that I've highlighted is make sure there are always enough threads to avoid stalls. Try and have a high ratio of arithmetic intensity, so try and do more compute than memory movement, because memory movement's always going to be the costly thing. Said at the beginning, really what we try to do with any kind of high performance code is minimize data movement. There are some clever things we can do to kind of utilize caches, but we don't really have enough kind of time to go into those in just another kind of 2-hour session. But I do have some slides I can share with people if they want to kind of look at a little bit more beyond the end of today. So here we go, we've got another example. Which decomposition will be good for device utilization? So we have a piece of code. I can't remember what this piece of code is supposed to be. So yeah, it's a 2D problem, I and J. So you can imagine it's an image 512 by 512. Some piece of code that we're doing is or some piece of instruction that we're doing is independent of each pixel in the image, and we can decompose it in two ways. So we can decompose it in 1 dimensions or 2 dimensions. Which is going to be best for device utilization? Is it going to be left or right? No. Say again? No. Yeah, you're totally right. Ignore that. I changed that last night. I changed that. It was the other way around last night. Then I changed it thinking, oh, that's wrong. How's that been wrong for so long? And then, yeah, no, that's why. It's because after we were at the pub. After we were at the pub. So. But this is good. This means that you're paying attention. This is great. So I'm going to dive into this a little bit deeper because this is a really important point, this idea of kind of oversubscription. So one of the ways that you can kind of think about oversubscription is via this metric that's quite often used when talking about GPUs called occupancy. So occupancy is the measure of the percentage of the maximum potential warps. That's a real mouthful. So it's basically active warps over the maximum active warps. Oh, I haven't told you what a warp is yet. So that's really important. So I said that threads act in sync, so they act in groups. They always act in these groups that are kind of clustered together, and that on an NVIDIA GPU is called a warp, and it has a fixed size. So it's a fixed size of 32. Yeah. Although it's a fixed size, technically it could change. The documentation says a warp is not a fixed size, but it's a fixed size. It's 32. It has never changed. But it is different on an AMD GPU. It's 64. It's different on an Intel GPU. It's 128. Is it, Chris? And it's got a different name. It's got a different name, but it's customizable. Yeah. Wow, there must be a minimum size though. Yeah. And it's probably 32 because 32 is a good number for computing. Yeah, yeah. The reason it's 32 on an NVIDIA GPU is the number of CUDA cores per streaming multiprocessor is always a factor of 32. Yeah, the warp itself is that group of kind of 32 threads, and it kind of acts in sim. There's some kind of slight exceptions to this. I'll go into that in a little bit, probably. Yeah, so you think about that diagram of string computing that I showed with single program, multiple data. All of the threads in the warp are performing the same instructions, caveated with some exceptions that I don't want to go into because it's a bit messy. But it's the best conceptual way to think about them is they're all executing the same instruction on a separate piece of data within the warp. Yeah, and it's the warps that are getting context switched. So despite the fact that you have a thread block that could be, I don't know, 1,000 threads, that kind of gets chunked up into these warps, and then within the warps, so within the streaming multiprocessor, you have as many warps as you can to fill it, and then all this context switching is going on, and that could be getting threads from the same block, or it could be getting threads from other blocks that have been assigned to that streaming multiprocessor. It doesn't really matter because they have their own kind of memory and registers and so on. So that's what a warp is. It's a really important concept. And occupancy is the number of warps that are active versus the maximum number of active warps. Yeah, so the maximum number of active warps is fixed. You know, it's fixed per streaming multiprocessor. There's so many that it can support. But the number of active warps can vary because of kind of resource restrictions, right? So when we write our GPU kernel, when we specify our block size, there are a number of things that can limit the number of blocks that you can fit per streaming multiprocessor. So if you write a program that's got loads and loads of register use, and then you set a really big thread block size, when it gets mapped to the hardware, when the blocks get assigned to streaming multiprocessors, if one block is enough to utilize all of the registers, then you can't put any more blocks on there. Yeah? Or if it's close to the number and you've got some left over, but you can't quite fit another block on it, doesn't matter. Only one's going to get assigned. That's an extreme case. But you get the idea. The size of the group, the size of the thread block can affect occupancy because it's going to affect kind of how many registers you use. It might also be restricted by shared memory usage, so that's not something that we're going to go into, but that is kind of use of a particular cache that's available on the device. Think of it a little bit like registers again. It's just a resource that you can use and specify, and it's limited per streaming multiprocessor or on the physical block size. Almost always, this occupancy is limited by either the registers or the block size. So it's a really nice way to have a think about occupancy is that there's this kind of this monster Excel spreadsheet that you can plug the numbers in. So the only numbers that you really need to know are which architecture it is. You stick that in up at the top. This is available if you download CUDA. It just comes kind of, or it's on the website. Put the architecture in, and that gives some instruction as to how many registers there are per streaming multiprocessor, how much shared memory there is, what the block size limitations are. And then you can put in the number or your thread block size, and then the number of registers per thread. So you can get registers per thread when you compile. You can put a switch in, and it will tell you it. What it does is it prints this nice graph, so you can see the impact of, actually, if I vary my block size, how is this affecting occupancy? Yeah. If I vary the number of registers, am I at a cliff point here where actually, and if you look at this example, see the registers are here, and you think, well, if I could use a few less registers, then look, we could jump all the way up here and do that. So maybe I could shift something out of registers into, say, like shared memory or something like that. Yeah. So it's a really nice way to kind of understand the implications of occupancy and, importantly, what it is that's limiting occupancy. So it's worth pointing out occupancy is really good because if you have high occupancy, you have more potential for hiding latency, because I said about that context switching that's always going on. If you have higher occupancy, if you've got memory-bound code, that's great, because all those warps that have said, go and get me something from memory, get context switch out, it means there's more potential to bring in another warp. There's more stuff available to context switch in and hopefully find useful work to do. Works to an extent. If you've got highly latency-bound code, as I said, you reach a point where you just become saturated and you're always going to be waiting on kind of memory. But if you've got memory-bound code, It's very good. If you've got compute-bound code, it won't make any difference, because if your warps are being kept busy doing compute, they don't need to be context switch out, and actually occupancy won't make any difference. Yeah. Generally, things are kind of memory bound, so it's a generally a good idea to aim to have a higher occupancy within your code. So there's a really clever way of doing this, and I haven't put it in the slides here because it's really boring looking at kind of API docs, but they are tagged on at the end of the slides, where you can see when you launch your grid of thread blocks, there's a call that you can make that says, pick me a block size that is going to maximize occupancy, and the API will just return back the number that will maximize occupancy. So as I said, it doesn't guarantee it will get you the best performance, but it's usually a good indicator that it will. So the next thing we're going to think about is code branching. So we've introduced the idea of warps, 32 threads in a warp. So this is where I said this idea again of single instruction, multiple data. We've got all of the threads doing the same thing. Yeah, it's not strictly true, because there's in kind of later generations, threads can have their own program counter, but that's not, they don't operate independently. Warps still execute the same instruction, but there is a possibility in later architectures that some sub-warp context switching can go on, just as an opportunity to hide more latency. But the simpler thing to think about a single program multiple data model is perhaps the simplest way to think about it. And it doesn't change the fact that divergence in code is still going to be bad. So what happens when you get to a conditional piece of code on a GPU is that condition is evaluated, and because everything within the warp's effectively doing the same thing, it's performing the same instructions, if that condition is evaluated to be true by all the threads in the warp, great, no problem. They'll carry on, they'll go through that condition, and they'll process the whatever happens when the condition is true. If some of those threads are false, then what's going to happen? Like, you've got a single program counter effectively. Like, do you evaluate true or false? Well, you have to evaluate both, and what happens is those threads in the warp that are that evaluate the condition one way need to be masked out. So they sit and wait for the instructions to take place. So they're masked out, so they perform the instruction, but they don't modify any registers or data. But highly divergent code means that all of those branches, all of those conditions potentially need to be evaluated, which is adding, well, it's slowing your code down, isn't it? Yeah. So how do we avoid this, right? You can't avoid conditional code, right, entirely, right? It's quite normal that you would have conditional code. The implications obviously can be quite severe, and it's important to understand, what's going to impact that. So, because things are broken up into warps, the way that they're broken up is by their position within the block, and it works on kind of the X first, if you like. So, if you're going to have conditional code, absolutely don't have a condition that's based off thread idx.x, yeah, because if you have something that is kind of conditional on that, then that's going to dictate kind of how many conflicts effectively you have within your warp. Fully coherent code can still have branches as long as all the codes follow the same path. So the optimization technique here is avoid interwarp branching wherever possible. It's always nicer with an example. So we have an example, right? Who was paying attention there then? This is a bit of a harder one. Which piece of code is divergent? Which is coherent? So I'll give you a moment to think it. So we've got to have a look at this. So we've got a condition. It doesn't matter what it's doing, but we have a condition. One of them is based off block idx.x modulated, and one of them is based off thread idx.x modulated. Which is the divergent code? Is it left or right? Right. Oh, wow. Yes. It means that effectively there is. I'm trying to think of a way to explain divergence without using the word divergence. There's a split. Yeah. So diverge means that there's a split. So if you have a condition, it means that some of the threads go one way, some of them go the other. Yeah. So this is this is potentially some divergence. Oh, I've given the answer away now. There's the answer. You were all right. Okay. So this is some divergence because we have a situation here where some of the threads within this particular, well, within this block, but ultimately within the warp, because this is based off thread idx.x, are going to be split. And some are going to go one way and some are going to want to do the other. So it means that we're going to have to evaluate both of these conditions so that that warp can finish this kernel. So it's nicer with a diagram this. So if we consider the divergent case, we have all the threads, and there's 32 of them here. Trust me, I've counted them. They're all proceeding as you'd expect. Same instructions, great. We hit this branch divergence, which is this, if thread IDX. So half the threads within the warp are going to execute the instructions. The other half are going to be masked off. And then after that, it kind of switches. So half the threads become masked off, the others become active again. They perform those instructions, and then the divergence ends because we reach the end of that, and they can continue through the rest of the instructions in sync. Yeah, but we've added some slowness because there's two conditions, so it's potentially got twice as slow. The opposite is block idx.x. So if we're kind of modulating on block idx.x, then we don't have a problem because all of the threads within a warp evaluate to the same value. Yeah, unless you pick some really, really small numbers, I think. But you wouldn't do that. So yeah, so this is an example where yes, we have conditional code, but it's still fully coherent, and we don't pay any performance implications as a result. Yeah, I've got the same slide. I'm not sure why there's a duplicated slide there. But so the next thing I'm going to talk about then. So do we have any questions on divergence? Because I realise it's slightly harder than the first two. Happy with that? Jack?
I might have missed it, but when the thread gets... I don't know if I missed it, but when the thread gets kind of switched off because it's diverging, how does it avoid operating on that data? As in, is it actually being switched off somewhere?
It's not physically switched off. What happens is each thread has got like a predicate, so it effectively gets masked out. So it just performs a null op. It just doesn't evaluate the instruction. The instruction, it still sits and waits. It just doesn't actually perform the instruction. It doesn't alter the registers that it yeah.
Because you're saying the wonderful thing about GPUs is that all of these things execute the same instructions in parallel.
Yes.
But that's also the drawback of GPUs. It's depending on what you want to do.
Depending on what you want to do, yeah.
So, but aren't you then breaking that drawback? As in, why do we have that drawback if you can tell different threads to do different things?
They're not doing different things. They're either doing it or they're not doing it. Yeah, and if there are two choices, you have to do both of them. Yeah, so the divergence means that the two paths both have to be evaluated. So
hence the delay.
Hence the delay. So all threads have to evaluate all paths. Worst possible situation is that you have within the warp 32 divergent paths. So each warp going in a different direction because there's some condition based off it doesn't really matter what it's based off, but you know, they could all be evaluating 32 independent paths through the code, and you would have to evaluate all 32. If you factor in, you know, that might not be simple compute, that might involve a memory operation that's hundreds of cycles long, you know, suddenly your piece of code that looked quite efficient has now got to wait 100 cycles on each of those conditions, which means whilst it's switched off, then it comes back, and then it still has to evaluate the other paths. So branching can be bad. It doesn't have to be, but it can be quite bad.
And so the threads that are masked off, do they not receive any instructions, or do they receive instructions and operate on dummy data?
I'm pretty sure that they don't operate the instructions. So the instructions there, they just don't.
They just never
evaluate it. Yeah, they just.
Okay.
Yeah, I think they're just predicated out. Yeah.
Cool. Thanks.
This happens because of the single program counter for the warp.
I can't answer that question without lying. So I'll lie and say yes. Yeah. So.
Can you repeat the question?
So for the yeah, go on.
So the question was, is this divergence happens because of the single program counter for the warp?
The simple way of answering that is yes. In later hardware, actually, there are separate program counters per thread. So historically, this is the case. Later, that has changed slightly, but the execution model still means that the same instructions have to be executed, even though there's a separate program counter. I have a really nice diagram that explains this. I wanted to avoid explaining it, which is why it's not in here. But so the simple way to think about it, to avoid too much confusion, is single program, multiple data. The reality is it's slightly different, but divergence is still bad. So what I've said still holds. Yeah. I can show you a different slide later if you'd like, okay, just for you. So what I was going to talk about now. So memory bandwidth, yeah. So this is obviously really important. Cost of moving memory is a lot. GPU is going to help us out. It's going to do this, you know, if we've got good occupancy, it's going to help us by masking that as much as you can. But what we really want to do is reduce the amount of memory that we have to move. If we move less memory, we have to mask less, which means we're going to get more compute, which means we're going to get better performance. Okay, right, so this is what the GPU memory looks like. Well, a simplified version of kind of what the GPU memory looks like. We've got host memory. When we say CUDA memcopy, host to device, it goes over here. And then when one of our threads says, get me something from memory, what happens is it moves and it goes via the L2 cache, always goes via the L2 cache, and then it goes potentially into one of these little local caches that's on the Streaming multiprocessor, and then it goes into registers so that the thread can access it. So this is the reasonably simplistic view of it. Sometimes this local cache, this L1 cache is used, sometimes it is not. It depends on a number of factors as to whether that is used, usually whether or not the memory is read-only, or whether we've explicitly told it to read through that local cache. I have a slightly more advanced diagram that shows that same piece of memory, and I think that's in a little bit later in my slides. So when memory is loaded, as I said, it moves through the cache hierarchies. It goes through L2, potentially goes through L1. What we want to do is something called coalesced access, right? So coalesced access means that when sequential threads from within a warp access sequential values from memory, then what happens is when we move data, and we never move it in single kind of units of data, we always move it in cache lines. When we move that cache line, it means that we're going to get good utilization of the data that exists within it. Yeah, so this is going to be much easier with a diagram, but the general optimization approach is to use a coalesced access pattern, which means adjacent threads in a warp or adjacent threads in the block should always try to read from adjacent places in memory. Or if not adjacent, then you should try and have good locality of access within memory. So this is much nicer to explain with a diagram. So I've got these not very nice diagrams, but at least it's a diagram. So we have these byte boundaries in memory. So these are 4-byte boundaries. And then you can see how an L2 cache line sits across that, and you can see how an L1 cache line fits across that. So L2 cache line 32 bytes wide, L1 cache line 128 bytes wide. So say we had a warp of 32 threads. If each of them wanted a 4-byte value, it would have to move all of this data here. And we'll see what that looks like in the next slide. So this is where this idea of the code that you write on the GPU can have quite big implications in terms of what's happening, because you don't really think about it. You think, I need something from memory, go and access something from memory. But the actual implications of that are quite, they require some understanding. So you need to understand, well, how is that memory actually being moved through memory? Because this can have quite a significant impact on the amount of memory that has to move. And we know that if we have to move more memory, we're potentially going to have more stalls because of all the context switching and occupancy and everything else. So here's our example. This is pretty standard. This is what we had in our examples yesterday. That is an equals. I don't know why. I've never found a projector that's shown kind of Courier New font to kind of look at that. But this is an equals. So we calculate an index, and we get some data. It doesn't, forget about output data, that doesn't matter. We'll think about the read. So on the read, we're reading from a unique position, and we've generated a unique index within our one-dimensional block. Yeah, so this is all of our threads. This is all the data that's going to move. This is really good. We're happy with this. We're happy with this because we effectively are using all the data that we're moving. So in L2, this is going to mean that we have to move 4 cache lines to kind of service this warp. We have to move 4 whole cache lines. But every cache line that we move, we're using the data out of it. So this is good. This is good cache-efficient code. We have this nice coalesced access because we're accessing we have plus thread IDX to X, so it means every adjacent thread within the warp is accessing an adjacent position within memory. It's lovely, yeah. Does everyone follow that? Yeah? Okay, so what happens when we don't do that? There are some things you can do that are fine, some things that you can do that are bad. So you could have permuted memory access. So some of the threads might access things that are nearby, but are not necessarily coalesced. Yeah, so I don't have an example where I can write this as code because you would have to assume that the index position is coming from some function, and then it's more complicated than just having a diagram. So there's something that's happening within our code that means that index, the position that we're looking up in memory, means that these get jumbled up a bit. Yeah, but if it's permuted within the same cache line, it doesn't matter. You know, we don't have to move any more data. We're not requesting data from over here or over there or, you know, miles down the kind of the memory addressing. So it's absolutely fine. Yeah, this is great. No performance penalty. Still using all of the data within our cache lines, so we're getting really good kind of bandwidth utilization. And it's okay if this happens. So if we permute across a cache line, this is also fine. Yeah, it's fine because we deal with warps. We don't deal lower than warps. We're guaranteed that with a warp, you know, if everything's going to want 4 bytes, you know, we're going to have to move all of those cache lines anyway. So if we have this permutation across here, then that's absolutely no problem. It won't cause multiple loads. We're moving the same amount of stuff. But what we mustn't do is permute over this boundary here. Yeah, because if we permute over there, we're going to have to move some more data, aren't we? Yeah. And we can see that with another example. So rather than having a permuted access, what we're going to have is we're going to have an offset memory access. So we can end up with an offset access if our memory addresses don't align nicely with the 32-byte boundaries that we have. And this can happen if you design data structures that kind of have bad alignment in memory. Yeah, so if your data structures have bad alignment in memory, then this can happen. So quite often what can happen is you can pad those to 32-byte boundaries so that you avoid that. Yeah. I don't think I have an example of this in the slides, but there are ways in which you can do that. So what we see with this offset then is we have a problem with the beginning of the warp and the end of the warp. So at the beginning of the warp, it's not too bad. We're using most of the data barring one piece is kind of being ignored. We have to move the whole cache line anyway, but then at the end we have to move a whole cache line and use only a single piece of value, single value from it. So we're having to do 5 transactions rather than 4, which means we've only got 80% utilization of the data. So this is bad. This means we've got more memory moves. This means that our context switching has to work harder. Given that most things are memory bound, it means we're probably going to end up stalling more than if we had something with better kind of coherent access and non-offset access. But it's not the worst thing we could do. The worst thing we could do would be strided access, because strided access means we potentially move a lot more data. Yeah, so here's the example of strided access. So we calculate a unique index and we times it by a stride. This means that for each adjacent thread, we're offset by the stride every time we kind of access into memory. And this is horrible, right? Because now we're only using 50% of every cache line. Yeah, and the worst possible case we could have would be a stride of 32, because we'd end up having to move 32 separate L2 cache lines. We'd only get like 3% utilization. It's going to be as bad as random access, Again, random access is not a good memory access pattern either for a GPU for exactly this reason. Yeah. So good locality is important. It's especially important to try and have coalesced access. What you can do is if your data is strided, you can kind of transpose it. Yeah. And this potentially is the problem with the code that we're looking at in Python, because this applies not just to CPUs, but it's not just to GPUs, but to CPUs as well. If you remember the difference between CPUs and GPUs, GPUs suffer more from these kind of poor access patterns because the caches are smaller. So we can much more quickly completely fill the cache memory and have to then go and kind of move more things. GPUs have to work harder, use the context switching to kind of hide the latency. CPUs are much better at masking this. They have more complex pipeline, but coalesced access is a good thing for both. Yes?
How much time you save by losing strided access compared to the time you take to perform transfers?
So the question is it better to do a transpose which costs compute than simply having a bad access pattern? The answer is it depends. You can do a transpose where you read and you write are coalesced, which is great because there's some So you can do a coalesced read and a coalesced write to do your transpose, so you can have an efficient transpose. But it does depend, obviously, on how much you're going to read from that data. Yeah, because if you're doing only a single read, then yeah, maybe not so much. The best thing to do is kind of profile it to understand. Yeah, but it's pretty typical that like the GPU accelerated BLAST libraries would recommend doing a transpose first. Yeah. Okay. And there's a nice graph that just kind of highlights what I've said. You can see that drop-off is quite severe, so it's showing the impact of stride versus memory bandwidth. So I'm going to summarize what I've said in this lecture then. So for good performance, there are certain things that we should consider. So the first is that we should try to minimize data movement to and from the device. We should try to minimize data movement full stop, but the first step is always try to minimize data movement to and from the device. We should ensure that device is kept busy by giving it lots of parallelism, give it lots of threads, oversubscribe. That's the model, that's how it works. Avoid conditional statements and branches in kernels. Not exclusively, but make sure you avoid them if it's going to cause divergent code. And align memory access to 32-byte boundaries. And as I said right at the start, these are general principles that you would try and utilize when programming GPU code, kind of even before that point where you get to profiling. Once you've kind of done those and implemented these, the way to kind of go further is to profile. There are other tips and tricks that you can use to try to accelerate your code. We're not going to go into those today. We're not going to do them in the hands-in lab because it gets into some more advanced topics. If we have had another day, the next thing that I would have taught you would be shared memory, which is a way to utilize one of the local caches so that you can move and exchange data from threads within a block. It's a really helpful technique for exchanging information, and it's the building block of kind of really efficient algorithms like matrix multiply. There are tons of more advanced things that you can do with clever warp approaches, and there's lots of opportunity for optimization, lots of clever things you can do. But generally, by following these principles, you can get pretty good code. Yeah. So, any questions? Save them for the hands-on labs. So, we have another hands-on lab. This one features a picture of my dog. So, I do hope you enjoy it. So, if you go to instancehub.com, and you'll see it on the list of labs that you had access to before. If you want to continue with the previous lab, that's absolutely fine. Come and see me and I'll add you on another credit. I'd suggest a good point to swap over is if you complete the first exercise. Don't worry too much about the second and third exercise in the first lab, but completing the first one is generally a good idea before coming on to this second one. Second one's going to provide you, so this one that's linked here. I call it the second lab, but it's got a number 3. the second one has got some existing code for you to work through, and what you're going to do is improve the performance of it by applying the things that I've told you about. Yeah. Okay, so we've got about 15 minutes before coffee break, so maybe make a bit of a start on it. When we get back from coffee break, then there's an opportunity to carry on with this, and what I could do a little bit later in that hour-long session is I could maybe, if people are interested, talk a little bit about shared memory and show a few slides on shared memory, if people want to. Yeah, we'll see how we're getting on with the coding, I think. Yeah. I don't have an exercise for it, but I can show you. Yeah. Okay. I'll stay mic'd up in case there's anyone on Zoom that's got any questions. Those people on Zoom, if there's anyone on Zoom, I'm not sure, but if there's anyone on Zoom wanting to do the hands-on lab, then feel free. If you don't have access, then if you go on, log in, you've not got access, then just drop a message and I will fix that for you. Right. Should we do another short little talk then on some more memory stuff? Yeah? Okay, right, let's do it. So I've called it advanced memory. It's not too advanced, but it is a bit more advanced than before. It's incremental. So all of these lectures, so in my previous job as a prof and a lecturer at Sheffield, I taught undergraduates about this, so I have quite a lot of material. So this is kind of like a condensed view, kind of extracting the bits that you can kind of condense into a couple of days. But I have, like 12 weeks worth of content spread out nicely across kind of 12 weeks. So there's quite a bit that you can go into. Yeah, okay, so advanced memory then. So we'll cover some of this. So we saw this diagram already. So this was the kind of the cartoon view, if you like, the simplified view of memory. So we have host memory, GPU memory, and then this doesn't have the L2 cache on it, but this is showing what we'd do is we go into L2 cache and then we would go into possibly a local cache and then into registers, and stuff always gets moved around then from registers. So I'm going to show a slightly more advanced view of it. Before I do, I think it's a good idea to kind of look at a GPU. So this is quite an old GPU, but it's a nice picture because it shows, the GPU on the board, which is quite nice. So this is a bit of a weird one because this was like a dual GPU card, so it had like two of them on one board, which were individually kind of usable, but you can see kind of the GPU DRAM kind of physically located on the board. So you get, this is why going to memory is slower, because it's physically distant from the chip. It has to come through the connections into the actual kind of silicon.
How many DRAM is there?
Oh, I can't remember. I can't remember. Sorry, it's an old card now. I haven't used one of those for a while. Not many people use these because there were this weird dual card thing that was quite hard to heat, and they tended to go for other devices. Yeah, but it was just a nice picture to kind of emphasize it really. And then obviously you see the PCI, so that system memory is kind of coming all the way from over here somewhere and then into the DRAM. So it just gives you a nice visual of kind of what's happening. All of the kind of the shared memory, the cache and the registers are in the silicon, so that's much faster. So obviously you want to keep things as close to the compute as you can. So here is the slightly more complicated view of memory then. And it's slightly more complicated, and it's also, it's kind of changed and moved around over time, and things have kind of tweaked and happened slightly differently in the NVIDIA world. So the fundamentals are the same. We still have host memory, we have GPU memory, we have L2 cache. There's these other areas within GPU memory that kind of do some specialism, and each of those is kind of a separate talk in itself, really. So I'm going to skip over a couple of them. And then when you go into threads, into registers, you've got these different caches available. So I'm going to talk about a few of these. So I'm going to talk about the constant cache and the L1 read-only cache. So this has become unified with this piece of cache called shared memory. So most caches are, you're reliant on the the hardware itself to do something useful with them. So, you know, memory is going to just move through them, and hopefully if you have good coherency, you'll utilize it well. Shared memory is the exception because it's individually programmable, so we can explicitly control what gets moved into it, how it's utilized, and that means we can explicitly control how things are exchanged between threads, which is really, really powerful, really nice and powerful model to have. Again, something that you struggle to do in, say, the directive-based languages don't really have a particularly good model for this, but because we have this kind of, the abstraction that we're using is kind of lower level, we keep that control at the expense of kind of coding complexity. So, yeah, I said that things have changed over time. So it used to be that some of these were kind of separate, and they've kind of changed, bits have kind of merged, and there were separate caches and then unified caches, and then there were opt-in and opt-out, but it's been fairly stable now since Volta. Ampere and Hopper are pretty much the same configuration. The size of the caches keeps changing. These L1 caches keep getting bigger because if you can pull things through those, it means you can potentially make your code more efficient. Yeah. So the first one that I'm going to talk about then is constant memory. So it's not used a huge amount, but it's a nice example of kind of how the GPU device memory can be kind of specialized. So constant memory, it's a separate area of GPU memory is used for storing constant values, and then there's a specialist cache that can be used for on the streaming multiprocessor when you actually kind of read things from constant memory. So the idea of the constant memory is that you use it, it's read-only, you can't write to it, but the idea is that you try and use it in kind of broadcast access. Yeah, so by that you mean that all the threads within the warp should ideally read the same value from it. That's going to give you the best performance out of constant memory. So what you can do to define something as constant memory is you just use the symbol. You just use this constant qualifier. Just the same as you use the device qualifier, you use the constant qualifier kind of globally on a variable within your code. Kind of causes somewhat of a problem in C++ code because you have to have this kind of global, which is a bit ugly. So it tends not to get used a huge amount, but it is quite useful for certain situations. So here is, again, an example of some code. One of them has nice broadcast access and one of them does not. Would anybody like to have a guess at which is a good use of constant memory? Again, that's an equals. So who thinks left? Who thinks right? Not so sure. Okay, right, let me explain then. So, good use of constant memory is this. So every thread within the warp is going to have the same value. They're all going to have the same block idx.x because in the right-hand side, every value of I is going to be different for every thread in the warp because it's based off thread idx.x. If every thread within the warp has a different value, then it means that constant, we're going to be looking up a different value. Yeah, so it's not a broadcast read. In this case, it is a broadcast read, so it's kind of one read request, which is great. So read-only memory then, so constant memory, it's very kind of, it's quite niche in terms of its use. Read-only memory is kind of much more useful, so if you're wanting to kind of indicate that something is read-only, then it gives us the option to bring it through the L1 cache. Yeah, so everything goes through L2 cache. We've seen what the implications of that are in terms of coalesced access. But if something is determined to be read-only, then we can bring it through L1, which means that we've got kind of all of the L1 cache space to utilize as well. Yeah, so that can be good, but it can also be bad, because if we have a bad access pattern, L1 cache lines are much bigger, 128. Those problems, those examples we had with striding and offsets, potentially that can be made much worse if we've got a really bad access pattern. If we have some locality, but it's not great, then it might actually turn out all right, because even if we don't get good utilization initially, if we've got lots of access via L1, then if the cache lines have already been loaded, then you might be getting some good use out of it. So the read-only memory is it's unified with something that used to be called kind of like texture memory. So if you think about the type of use cases that you'd have if you were reading a texture, which are effectively an image, same as what you'd do if you were kind of writing graphics code, is you have good locality, but it might be kind of in multiple dimensions. So you might kind of want to move multiple cache lines around that have got reasonably good locality in 1 or 2 or 3 dimensions. So that's a similar kind of use case here. So the way that you can do it is you can do nothing at all, and the compiler might actually determine that your code is read-only and pull it through L1 anyway. So that might be just something that happens. Yeah? Or you can hint to the compiler that you would really like it to do this, and it won't necessarily do it, but you can hint to it and hope that it's listened to what you said. And the way that you hint to it is you put this const restrict keyword on your pointer, and that's a good indication to the compiler that it's going to be safe to be able to bring it through the L1 cache, through read-only memory. Yeah. It doesn't guarantee it, but it's a good hint to the compiler that it probably should. If you want to check whether or not it has, you have to kind of go into the profiler and kind of dig into it a little bit more, which is quite advanced. Or you can explicitly use an instruction called LDG, which will force it to kind of come through a particular, through the L1. So shared memory is the one that I really want to talk about. So the other two are great, but read-only memory, generally the compiler is pretty good at guessing whether or not it should use it or not. Shared memory, though, is something that's much more powerful. So it introduces the idea of block-level compute. So at the moment, we've had this model of move data to the device, do some compute, and then move data back when you're finished. Shared memory adds another level where now we can move data to the device, and then within our thread blocks, we can then move data into shared memory and hopefully do lots of compute on that data that's in shared memory, possibly write it back out to the device, possibly not, maybe it's just a read-only thing, but eventually then kind of move stuff back to the host at the end. So introduces this idea of block-level computation. So it's not just another cache, it's user configurable. Because it's user configurable, we're going to have to manually load things into it, and we're going to have to also think about synchronization, because if we're loading things in, we're going to potentially have warps at different stages. We want to make sure that if we're loading things in, that everyone's had a chance to load things in. But it's very, very fast. So this is the idea with block-level computation then. Move things from device memory into our local shared memory, do loads of compute on it, and that means we don't have to go back out to device memory quite as often. Yeah. So here's a case for shared memory then. So have a little look at this. This is just like the blur example that you were working on the previous exercise, so on the notebook that you've been working on, except that it's a simplified version. So it's just a one-dimensional blur, if you like. So what we're doing here is we get a unique index. We create an integer called left and right. So we load the value at I-1. So from the unique index, we go kind of look at the value previously, and then we get the value to the right, and then we get the value at the index position I. So we're effectively doing 3 reads, and then we're writing a value out. Yeah, we're not doing a blur, but we're doing three reads in. We're not averaging or anything. But so for the purpose of this exercise, like it's potentially a good case for shared memory. So it's a good case for shared memory because we've got multiple threads kind of reading multiple values. Yeah. So one option would be bring it through L1, bring it through read only, and hope that we kind of hit the cache whenever this kind of thing happens. But we can do that more explicitly and have more control with shared memory. So 3 reads. So at this position here, we're reading something that you would expect our adjacent thread to have read. This position here, we're reading something that we would expect an adjacent thread to have read. Reading something here, perhaps we could share that with the threads left and right of us, and then each thread only has to do 1 read rather than 3. Yeah. Seems pretty sensible. Okay, so the way that we can do that then is we can use shared memory. Shared memory has another one of these kind of qualifiers that we use called shared. You can only use this inside a kernel, so unlike global, which we specified with a global scope, this has to go inside the kernel, and we have to specify the size. We can do this dynamically, but I'm not going to go into that today. For now, we will just explicitly define the size, block size. Yeah. Because this is compile time, we have to have a way to do it dynamically if we want to kind of pick. But for now, we do it explicitly at compile time. So there's lots of potential for things to go wrong here, right? So there's lots of potential for race conditions. So we're going to have to do some things to be very, very careful. So first of all, if we have a block-sized piece of shared memory, yeah, we need to make sure that we don't write beyond the bounds of the block. Yeah, we're going to have to make sure that if we're writing to shared memory, threads within the block, and we're talking block scope here, not warp scope. Everything happens in warps, but shared memory is something on the streaming multiprocessor, so it's a kind of block level resource. Yeah, we need to make sure that every thread within the block doesn't kind of overwrite a value from another thread. Yeah, we're going to have to make sure that we have some synchronization primitives so that if we say everyone put something in shared memory, we need to make sure that we say, have you all finished? Have all the warps that are within this block finished doing that? Because otherwise things might start reading before we're guaranteed to have filled it. So there's lots of caveats to look out for here, lots of things that we're going to have to do. So the primitive we have for synchronization is sync threads, and this is a thread level synchronization primitive for the block. Yeah, and this will guarantee that all of the warps within that block have reached that point before they're allowed to proceed. Important, but obviously that may add some latency. If we have too many of these things, it means that we're not going to be able to context switch and find good work if we're kind of stuck waiting on a synchronization all the time. So that same example has now been populated with some shared memory examples. It looks a little bit more complicated, right? I'm just going to turn that light off. It looks a bit more complicated now. Oh yeah, cheers, Tom. And it is really. It's we're making the code less readable for the benefit of kind of squeezing some more performance. So this is pretty typical of CUDA code, and part of the reason that other languages are perhaps better for maintainability and kind of portability. But if we really want to squeeze that kind of extra bit of performance, this is typically what we have to do. So here's what we add in then. So I've added it in bold so it's a bit clearer. We've added some shared memory. We've said that it is block size. Spotted something that is obviously wrong with this. Hang on. Yeah, no, there's nothing wrong with it, it's fine, okay. But it's a good point that I'm going to make. So we've allocated some shared memory that is block size, right? So the first thing that we're going to do is every thread, and we know that it will be every unique thread within the block because it's based off thread idx.x. Every thread within the block is going to load into shared memory. Given its position in the block, that means that the index is not going to exceed the length of the block. We're not going to go beyond the bounds of this shared memory. It means that every thread within the block has got a unique position to write to, so we're not going to have any collisions, we're not going to have any race conditions. Everyone's got a unique position to write to, and it writes to it given it writes the global value that it's reading from memory into this kind of shared memory position. We then call sync threads. Means we've got our synchronization primitive. Means that by the time we get past this point, we're guaranteed that we've fully populated shared memory. Yeah? Everyone still with me? Okay, cool. So code's exactly the same as before, but we've had to kind of specialize it a bit, right? So we've had to add this condition in here. So if we're looking left, yeah, then we're going to have to say, well, actually, there's a special condition here, because as long as our thread IDX is greater than 0, then we can look into shared memory, can't we? Yeah, if our thread IDX is 0, we can't do that, because we'd be looking at position -1, right? And we're going to be, that's not going to work. That's going to be, something bad's going to happen there, and it's actually undefined what happens. So, maybe your computer sets on fire, maybe, who knows. Generally, it'll just give you the wrong result. Yes?
Isn't it sort of poor branching performance to check
Of course it is. So I'm contradicting what we said earlier. So we've introduced, so the question is, this question was a comment. You've introduced a branch. You said branching was bad. I did say branching was bad. So this is somewhat of a trade-off, right? Because we have now introduced effectively a boundary condition within our code. Yeah, and this is one way of solving that boundary condition. There are other ways that we could perhaps avoid a boundary condition, but I will tell you, not going to show all of them, but I'm going to allude to what some of those other options might be in a moment. Yeah, but you're absolutely right to spot that we have a branch here. And what this will mean then, if we have a very small block size, then it means we've got a branch where, if the block size is small, then we have a branch where kind of every warp effectively is going to end up evaluating this, or is going to end up divergent. Yeah, if we have a reasonably big block size, it's not so much of a problem because only the one on the left and the right is going to have a problem. All the ones in the middle are not going to be divergent. They're all going to hit this same condition and load from shared memory. So we can optimize our code here by picking a good value. We pick a big block size, we have less divergence. But if we go too big, we're going to hit a problem of not achieving good occupancy. So this is where this idea of, looking at the occupancy calculator and now understanding and balancing these two things is going to come in. So yeah, so this is what we've done. We've specialized our code. We've done this for looking left. We've done exactly the same for looking right, because obviously we can't go beyond the bounds of shared memory. And then, of course, the value that we read initially, we can just pull that straight from shared memory. Or we could have stored it in a register and then put it in shared memory. I suspect the compiler would probably do that anyway behind the scenes. So, yeah. So, everyone follow that? Seems fairly sensible. It's a bit ugly, a bit more complicated, but it is more performant. I don't have some specific performance figures for this, but you have to take my word for it. It's more performant. Oh my word, I don't want to talk about shared memory bank conflicts. Absolutely not, no. So in the example we saw though, we introduced boundary conditions. Yeah, so we have global loads. I said that we can avoid that if we have kind of big block sizes. We can minimize the impact of it, not avoid it, but minimize it. But this is going to be even more prevalent in like a 2D example. So if we have like a stencil operation, then you've potentially got boundaries in X and Y. If we're a 3D problem, you've X, Y, Z. So the code can end up getting like a little bit ugly with branching conditions. So it's perhaps I thought I was going to present some examples as to how to avoid that, but I actually haven't. So I'll just tell you what they are. So one thing that you can do is you can have a halo region. Like, so this is no different to kind of what you're going to do if you're using distributed code now. If you're using MPI, what you can do is define a halo region in shared memory, and then you're going to unbalance your workload slightly because you'll say, okay, well, the thread that is on the left-hand side, I want you to load 2 values, and you load the halo region. If your halo region's big, then you can have multiple threads towards the beginning of your block load, multiple values in. But if you preload them in, yes, you add some divergence in a different place, but it means that you can have all of the memory available then in shared memory. So there's a bit of a trade-off. Yeah. If you're reading from shared memory a lot, it's better to have that divergence in the load, and then your reads are kind of constantly quite good. Yeah. Okay, so that's shared memory. I don't have an example for you to do on shared memory. I do have an example. I don't have it in a notebook or anything for you to play with. Casper, yes?
Could you go to the one slide back?
You can get a mic or I can shout. You got a mic, go on.
Okay. So my question is, in that example where size of S data is a compilation time,
yes.
Is there a way to have it dynamically sized?
There is, so I said slightly earlier, there is a way to do that. You have to be able to do it dynamically. For the purposes of just this simple example, I've done it at compilation time. But yeah, what you can do is you can, so if you make this this shared memory, when you declare it, if you say that it's a pointer, yeah, then it becomes dynamic. And what you can do is you can specify that size as an extra parameter in the kernel launch parameters. So you put block size, grid size, shared memory size, okay. Yeah, and you can do it dynamically that way.
Okay, thank you.
It's okay. Any other questions? Okay, fantastic. Right, well, I'll pop the lights back on, and I suggest we've got another 15 minutes if you want to keep having a bit of a tinker with that exercise, or if you want to ask any more questions, good chance to just grab just over the last 15 minutes or so before we go into our next talk.